Let's resume from where we left off in the last video. I've been going over the old Spinal project, and if you go into the project file, you'll see all this stuff. And here's the ML library. We also have the Leduc game and no limit heads-up hold'em games implemented. And this is a GPU implementation, by the way. There are a bunch of tests. I actually tried running the web UI. It can be done using Ctrl-Shift-B to run the tasks. I had to install Poetry, install the packages. It actually ended up downgrading NumPy in my main environment. And this actually exists. I tried running, for example, the rock, paper, scissors game, but when we tried running it, I think the CuPy library isn't installed, so that's why we're getting this error. So yeah, pretty much, I'm kind of assuming that everything is broken. I don't really want to fix this right now anymore. Like, these games are pretty much dead weight at this point, and I see no point in trying to bring them up into shape. Instead, our goal is to implement the basic algorithms, to do the easy stuff. And I want to leave the web UI aside and maybe just focus on, just doing this thing. Like, I don't want to think too much, so we can just dive in and start programming. We can paste whatever we need from the old library, and then implement the Leduc game that way, just by copy pasting the old stuff, and then implementing the numerative CPR algorithm on top of it. So the way we'll start off is just by making this Hopefield dictionary, Hopefield dictionary folder. It has to be with an underscore, and the machine learning library and everything else, we're going to just get rid of it eventually after we're done. Maybe I'll leave in the tests, but this is going to be just we're just going to leave this aside, and it's going to stay there on an old branch somewhere. So let's see. Okay, let's also make the game folder, and we're going to make the Leduc folder. And okay, let's start copy paste. Let's start by copy pasting this union card nominal deck. Okay, whatever. Base. We have to wait a little so the link gets created. It also helps to, instead of just waiting to make a change to the file, that way the Visual Studio Code editor will recognize the change. Let's close this. Yeah, we're starting a whole new chapter in the book, so it's not bad to just reconstruct everything from the top. Now comes the card module. Let's also make the deck module. The module. It's just converting the integer to card. The deck, let's see. Let me think. This is taking in. Okay, this is returning an integer. Oh yeah. This thing. This is. I mean, I can just show you what it is. Let's start. Let me start an F# script. Where do I start it? The equals, let's see, that's 1 to the power 6. In other words, actually, it's 1 shift to the left 6 times, and that's the same as 2 to the power 6 minus 1. And if we run this, oops, it should be Alt Enter. Yeah, that's 63. And 63, okay, how do we turn an integer into binary? How do I turn an integer to binary in F sharp? Okay, let's try this. You can just press control period to, and it will often for these system functions just offer to add them in automatically. Okay, so let's convert this integer to binary, and maybe actually I think this is a bit. These are too many cards in the deck for something like Leduc. Maybe we can make this a little bit better. Yeah, so this is 111. Oh, so it's exactly 6 cards. Oh, nice, interesting. Yeah. Actually, it makes sense. If it was no limit, if it was no limit hold'em, let me just bring the mic a little bit closer. If it was no limit hold'em, it would be 1 to the right, shifted left 52 times, and that would be the full deck. And this when we shift this to the left 6 times, that is enough to cover only 6 cards. So yeah, that makes sense. There are 6 ones here. Okay, that makes sense. Can we actually do this operation in Python? I think, yeah, we're going to have to try it out. It's also opening random, and this is core Cuda. Okay, I don't want that. And this is Cuda intrinsic. We don't want that. So yeah, I guess we have to be careful which backend we're using. Okay, so this is the first thing that we need to figure out, how to draw cards from a deck in a generic manner. And this thing, this only just draws more than a single card. Let's see. This is the CUDA random number generator. Okay, let me pause here so I can think about it. I guess it's going to take some time to be able to do this. So the best we can do is maybe start step by step. Okay, let's get rid of this. Let's get rid of the core CUDA stuff. We don't have the intrinsic. We don't have the random. And now all of these are type errors. So what exactly shall we do? Let's test this one by one. Okay, let's see. Main, and we're going to test things one by one. So okay, let's create a deck. Let's see what happens when we do that. you know, deck. All right, create. I mean, spiral build file. Oh, deck M has a type error. Summary step path. Yeah, of course it does. It also has a type error. I mean, yeah, let's comment them out for now. We have built the file, deck mpy. This is how it looks like right now. The kernels are empty, and what you see here, it actually in the newest version of Spiral, which is in pre-release right now. Let me just show you what I'm using. Yeah, this is the pre-release, and I started work on it while I was working at Tower City, so I didn't have the time to really do a proper version of it, and it basically has this work in progress native CUDA backend, and I'm not even sure what exactly is in the change log. Well, let me take a look at it really quickly. Where is the change log? The new macro prefix. There's some inlining stuff for the CUDA backend. Change the data that the backend join points return. I have no idea what that is. Oh yeah, I think I changed it from an integer to something else. I'm not sure what it is. In order to separate out the core library from generated output and reduce code noise, the CUDA backends with the return. And basically, they're outputting two different files. Let me just show you. And you are already seen it. It's basically this. When we compile a file in the Python and the CUDA backends, I mean in the Python CUDA backend and the native CUDA backend, it creates this decem auto file. And this is basically nearly completely static, and it has a bunch of these core library functions. And it's kind of easier to do it like this because now in the main file there is less noise. So I like that. Remove the old CUDA backend. Replace the Python uses with new generic C++1. Oh yeah. The Python backend had a CUDA specific backend, and I've merged the new. I created a new C++ backend that is polymorphic between host and the device. So that's what the Python backend is using now. I basically factored them out, and it's nicer to use. I mean, it's easier to maintain for me. I mean, new assert h to the h automatically imported in the core library, and if on def is placed to ensure compatibility with NVRTC. Okay, let me just see real quickly. Okay, this is the core library source. Oh, wait, then there's a plugin. Yeah, what I'm talking about is this thing here. Yeah, so that's what I'm talking about. And this default int and default unsigned integer automatically gets changed by the compiler if the default integer is something else. I'm actually using a regex match inside the compiler to do this. I have the same thing. Yeah, this is the Python library. It gets inlined into this decem auto file. So and this over here is also inlining the CUDA core library. I see. So everything here is everything in this core lib cuh file, Cuda header file. Okay. Let's see. The core libraries have been appropriately named. The reference counting cuh has been changed to core lib Cuda header. The counting py has been changed to core lib py. Fix the compilation Cuda virtual closure structures on the device by generating them programmatically instead of having them be default. This not will revert this change after NVIDIA fixes their compiler. In fact, that's kind of maybe interesting. Cuda dev. Can I sign in? Okay, let me pause here so I can log in. Okay, let's go here. Actually opened an issue on the Cuda support page for this. Yeah, because the way I was compiling them previously in the Cuda backend, that is the way I was compiling the virtual destructors and constructors was resulting in illegal accesses. So this was like 6 months ago, 6.5 months ago. And now if only this would open. Let me pause for a bit. Okay, it seems that there's something wrong with the NVIDIA backend, and I cannot actually open these. So never mind. It's just a little compilation change to fix the issue. And they said that they would fix this in a future version of the compiler. Yeah. Inside the compiler, I was using a third-party order dictionary, and in .NET 9, that was replaced with the inbuilt one. Here we have the unsafe backend switch. It's only to be used if it won't result in type inconsistencies. Remove the main body from the native CUDA Python backends. The device synchronization was causing screen flickering and system instability due to premature freeze when combined with the debugger. Oh yeah. So what this means is that previously there was a CUDA device synchronization inserted automatically by the compiler, and the reason why I had it done like that is so it traps the exceptions that get raised on the on device kernels. But eventually I figured out when I tried debugging some device kernel code that this would cause the GPU to crash because there would be some premature freeze being done. Like I would pass an array that into a kernel, and then when the main body finished, that would get freed, and then there would be a device synchronization, and if the debugger is still running inside the kernel, that would cause pretty bad issues. So yeah, that's pretty much a breaking change, and we shouldn't compile all the spiral code that depends on that. Okay, I'm actually going over the changelog, not for your sake, but more for my own sake. Yeah, I need to also test whether the new CUDA backend works. Yeah, I messed up and skipped a minor version. Okay, that's nothing. Okay, I'm not sure whether I actually want this. Fuck it. Let me remove this because I'm going to forget that this needs to be done. Okay, no problem. Yeah, I'll forget. I'll forget about. Okay, so this is creating the deck. Let's try maybe indexing into it and maybe toggling it. Let's also try printing it. Like, how does even console print work? Print x, print ln. Open console. Maybe open for ext. Maybe write ln. So it has console, right? What about? Yeah, let me check out the module to see how printing is done. Console Python. So it's underscore ln. Yeah. Okay. I see. Let's try toggling. Wait, what exactly is toggle supposed to be? Or right, we cannot print out a function that's going to cause an error definitely. Support a type. Console Cuda. Oh, why is it going in console Cuda? That shouldn't be happening. Okay, let's try toggle 0. And this is going to be index 0. Yeah, it's going into console Cuda, and I think we should have the Python plus Cuda backend selected. Yeah, let's actually open this error text file. Are we going to be pasting the stuff in it? We're also going to pin it. Pin Control K, Shift Enter. Control K, Shift Enter. Okay, that's pinned. Control K, Shift Enter. Okay, so write ln. Let's comment this out, and we only have to basically print this out. And this is this is a deck. All right, I thought it would be an integer, and if you recall, we kind of got rid of the prototype instance to print it. Okay, so let's go back into this Leduc deck m, and then we're going to bring back the prototype instance. Just where's the type for it? I mean, is it in base? Open core ext, open console. Really? Core base, core Cuda, cardem. So it's either in core base or core Cuda. It's probably maybe in core base. Okay. The way the printing works in the Spiral core library, I mean, in this particular core library, is that we have the base here, and we should have the prototype for, we have this prototype printable, and it gets passed in a record, and then you can just hit one of these functions, write ln or write to print it out. And we don't really have overloaded, how do you put it, classes like in .NET. So we cannot really override the toString. Instead, we just have this. And in fact, instead of printing this out, we should probably convert it to a string. But that has its own issue because this was intended to also work on the GPU. So we have to write it out into the buffer. We cannot really allocate a string on the heap on a in a GPU kernel. That would be very slow. That's why it's designed like this. It's primarily designed with the GPUs in mind. Okay, so let's see. So I think yeah, now it's printing. And we can try running it like with the Shift Enter. Oh yeah. Because if I put it in like Shift Enter, oh, I thought it wouldn't work, but it did. I mean, suppose I did this. But yeah, it doesn't seem like it's running it directly because it kind of gets stuck on this print statement. But maybe there is a Python run find to file in terminal. What the hell? I was trying to run it in this thing. Let me close this. I move this to the top. Oh, yeah, this works nicely. Let's try this out. We'll build the file. We'll run the file in the terminal. Okay, so this works. Now, how do we draw a card in Python? Okay, what we're going to do is okay. I've been doing research, and it's. I mean, it hasn't really been successful. Much more successful than our first perplexity query. I also tried Gemini, but its answer was absolute garbage. Let's see. Claude is trying to be very helpful, and I don't know, this does kind of look decent. And if I look at these masked bits, and I mean, okay, this would work. Count plus one, count equals offset. Whatever. I guess this is good enough. Find and set bit. So I guess we're going to have to maybe reimplement this in Spiral. Okay, how would we reimplement this in Spiral? Find and set bit, mask base offset, mask U32, base U32, offset U32. I guess this needs to be an integer. Okay, that's fine. Who cares? Uh, we also we have a count. Count equals 0. Let's make this 32. I mean, no, we don't need to put the type on it. Okay, now we have what we need is a loop for from 0. No, actually, yeah, from 0 near 2 equals 32 minus base, and then on I, yes, it has to be like this. And okay, if masked bits, then we need to increase the count. Let me just make it a reference. Really? I mean, don't we have a reference? Maybe we don't. Instead, we have to make a hippie mutable. Yeah, it's like this. How the hell is this done? Maybe I should ask Perplexity how to actually set a mutable variable in Spiral. I wonder what how it will. Oh yeah. I need to actually do count and instead of mute. For fuck's sake. Uh, mm, Greater than 0. Let's make it I32, whatever. If count equals offset, then what? We have to return the base plus I. Of course, we don't actually have a return operation in Spiral, but we can just put in something like a join point. One way of doing that is just putting this like here. But if we also want to have these variables be runtime variables, then we can just convert the inline statement into a let statement. And then over here, let's just use a macro return. It's not very spiralic, but whatever. And the return type should be what? Something like either an int32 or an unsigned int. Okay, let's make it an i32. So, oh yeah. Yeah, I mean, this is one of the disadvantages of using imperative loops in Spiral. Let's okay, how about we do this? Solution, and it's going to be limit max. And let's set the solution to what? Base plus 1. And it's what? Then we'll dereference the solution here. And if the solution is set, we can also just do a break here. And why is this a problem? Yeah, we need to get the count. And count is this also needs to be I32. What's this? This is I32. Okay, let's make it also I32. Let's make all of these I32, whatever. Unfortunately, the solution. Let's make it mean I32. Because the mean I32 in is also like the largest number when converted to binary. It's exactly going to be this. So yeah, this should work. And this implementation is actually less efficient than it would be in native Python. It's kind of it is awkward. We could maybe improve it, but by not using a heap mutable for the solution and for the count. How could that be done? Like if you look at the loop. We have these set and what? I mean, I guess we don't need get. Okay, so we have the dupe and the set. We'll make it this not equal 0. We just make this C. So we aren't fetching from global memory twice. But you know, this is fucking Python, so it's pretty much fetching from global memory everywhere, all the time. Yeah, the problem, we could probably implement this using native variables, but when using this sort of approach, I have run into issues with the optimizer, sometimes optimizing the set variables away. So that can be complicated. So it's best that we can avoid it. And the efficiency isn't really that important here, so we can get away with it. It's too bad. It's too bad that we don't actually have stack mutable variables in Python, or maybe we do. Maybe we have stack mutable. Oh, we do. But I'm not really sure whether the Python backend supports these. So I think it's only supported in the Cuda backend. Let's see. How would we even? Well, Vax is a keep layout type. Wait, what the hell? I think the description for it is wrong. Let's edit it. Let's fix it in the core library. And if I search for No, it didn't work. Okay, let's search it throughout the entire library. No. Wait. Maybe it's a unary operator. Oh, I see. I see. So it's like this: keep layer type, keep line type, creates and access, keep mutable layout type, stack mutable, stack mutable layout type. The description here is wrong, so we can fix that. But we won't use that way because, as I said, the Python backend doesn't support it. So now we're going to have to test this out and see whether it works. I'm also going to have to reimplement this sample masked bit. Okay, first, let's see. We toggle this. Okay, let's make a new variable equals. Now let's comment this out. Find and set bit. The mask is y. Well, let's make this a mask. The base is 0, and the offset has to start at 1. And in fact, I'm not really sure whether it's that way in Cuda, but never mind that for now. It's the deck. Okay, let's remove the mask from the deck. Oh yeah, it's an unsigned integer, unfortunately, and that's very annoying. So what do we do? I mean, whatever. We can just convert it to an integer here. Convert. There are like only 6 cards in the Leduc deck, so we can get away with using this. If it was no lead hold'em, we'd need to use 64. We need to use the larger integers, so I guess it's fine either way. Let's close this, close this, close this. Then let's build the file. Plus mute. V0. We can see where it's getting applied. By the way, having this many intermediate statements in Python is really awful for performance. If it was any other language like C++, Java, this will get optimized that way, but Python is bad when it comes to this. So our program is definitely going to be slower in Python than it would have been had we brought the program in it natively. So there's a mnemonic syntax. And yeah, that's because it's trying to run it in Python directly. 5, 1. Okay, let's also toggle the second bit. In fact, no, let's not do it like that. Let's toggle the third bit. Over here we're toggling the first bit, which is at index 0, and that index 2 is the third bit. Let's try finding the endset bit with the offset of 2. And I think that should be at the third position. Build, run. That it doesn't seem like it's working. Let's also print out the binary representation. Bin n. Okay. Python is pretty good when it comes to various utilities. You have to give it that. And I think this returns a string instead of integer. Let's build. Let's run. Yeah, so you can see this is how it's represented in binary. So this is 0, 1, 2, 3. So why is it not working? Wait, the solution base plus 1. Okay, yeah, that makes no fucking sense. Yeah, it's supposed to be base plus I. I probably misread this part. Let's build it again. Let's run it. So it's saying that it's 4. So this is what? This was what? 1? Let's see. Let's try the offset. Oh, yeah. Yeah, the offset has to start at 1. Then if we run it, we get 3. And that's not correct. If the offset starts at 0, okay, who knows exactly? Let me pause it so I can think about it. I figured it out. And basically, it's this line here that's different from the Python version. Like in Python, we increment the count, and then we check the offset. So the offset has to basically start at 1. But over here, we get the count, then we increment a separate mutable variable, and then we check it with the original count. So the offset starts at 0 here. And actually, this is a good time to maybe do a little bit of research how exactly the FNS instruction really works on Cuda, because I pretty much forgot then, and it would be good that when we run the game on a GPU in the future, that we make sure that the Python and the GPU implementations are identical in functionality. Intrinsic. Yeah, we just need to check this FNS function. Okay, so what do we do? I think I'm going to actually, it's going to be a good time to actually test out the new Cuda backend. I wasn't really intending to do it right now, but we might as well do it. We have, yeah, pretty much everything that we have all the functionality to implement the draw card. We just need to do the sample masked bit. We might as well figure out how it works right now, because I've definitely forgotten. So I'm going to comment this out because I don't feel like doing backend switches. And instead, let's figure out how to actually run a CUDA program again. So let's see, we have a bunch of tests. Okay, here's test one. Can we even compile this right now? I think this was the test that actually triggered that compiler error. Okay, I don't want to. No, I want something simpler. I don't want to. I want this. Okay, this is, I think, testing serialization. It's a testing how to print out this union type. Okay, I just want something simpler. Simpler. Is there a hello world somewhere? Let's make test 20. Just copy paste this. And what? Let's make this a hello world kind of thing. Hello world. Let's build the file. Now let's see what's happening here. We have this. And if we try to run it, what would happen? Non-type object has no attribute split. Yeah, it's not compiling. I have Cuda 13 SDK installed, and I need to install CuPy for it. Let's see, CuPy. Get started. Oh, wait, this won't actually work because pip command not found. Instead, I have the UV package manager, so I need to do UV pip. And maybe later I'll remove poetry from this project and replace it with UV. Okay, CuPy has been installed. Let's try running this again. Hopefully it will work. Wait, it's also trying to include Thunder Kittens. Wait. Okay, that's something to fix, but it won't really break the program. Let's build. Let's run. Wait, why did we get a warning? CuPy might not. Okay, let's try uninstalling the old one. UV pip uninstall. Okay, now let's try running this again. CuPy has no attribute raw module. Oh, for fuck's sake. Okay, what the hell is this? I mean, did the library maybe change raw module? CuPy has an attribute raw module. I mean, what the fuck? Let me do a search for this. What the hell? My path is not set up correctly, so CuPy cannot find your NVCC. Let's see, NVCC. Okay, so maybe I need to set up some kind of a path. Let's see. Uh, okay, what's going on here? Oh, all this crash. CC, CC, user local Cuda bin NVCC. Okay, let me just copy paste this into here. Let's turn on word wrap. User local bin. No wait, user local Cuda bin. Okay, yeah, so it's supposed to be there. So what exactly is okay, let's ask Perplexity what the hell it thinks. I think I mean, CuPy has no attribute RAM module. That doesn't really sound like it cannot find NVCC. Mm, I try. What is going on? So annoying. Also not. What the hell was this? Okay, I think. Okay, what I think is going on is that it was somehow probably using an old version of the module that we just uninstalled. And when we try running this, it kind of tries looking for the old definitions and cannot find them. What I'm going to do is close the editor and then reopen it. Now let's see whether that fixes it. No, it doesn't. What the fuck? Core. I mean, fuck. Okay. Maybe we just need to reinstall CuPy. Okay. You. Wait, it says that it cannot resolve it. Now let's try installing it again. Let me just make sure that I'm doing everything correctly. I mean, yeah, and it also does say that we need these Python pip install setup tools. Okay, let's do first this first UE pip install setup tools pip UE. Okay, now this seems to be working. Oh fuck! Thank God. Now let's go. Let's compile this again. Mil file. Then we'll run it. For fuck's sake. Okay, I'm going to pause here and come back when I resolve this. This is so fucking annoying. Okay, I managed to figure it out. I even opened an issue on the CuPy repo. It's pretty much this. And the solution is to just set the NVC environment variable to this. It turns out if we did what, where is it? Yeah, it's basically supposed to be a command to print out the configuration of CuPy. And if you look here, this NVC path is set to none, even though it's directly in user local Cuda bin and then NVCC. So of course, now that we go through that issue, we have another issue to go through, and which is invalid cluster size. And I think the cluster size was set for what? It was set for the H100 cards that I had access to while I was working at Tau Ceti as a contractor, not a full-time employee. Yeah, I don't want to imply. I mean, that's what is said in my contract, so I cannot really present myself as an employee. So let's see. Okay, so blocks per grid, blocks per cluster. So it's set to. Wait, what is the GPU set to? RTX 5080. The cluster size. I mean, blocks per cluster. There should be blocks per cluster, I think. So, okay, let's see directly here. 84, 256. Yeah. What exactly is the problem here? If we, for example, set it to 1, would it run then? Yes, now it runs. If we set it to 2, if we set it to 4, this it takes a while to compile. If we set it to 8, invalid cluster size. And that's weird. I thought that I tested it and it supported a cluster size of of 12. But who knows? I didn't. It's not like I ever really tested it thoroughly. Like, okay, it's very weird that it wouldn't even support a cluster size of 8. And this is a pretty small cluster size compared to something like an H100 card. I think I even opened. This was an issue on the Cuda forums that I opened once. Uh, and over there, it was explained what the issue with the cluster sizes was. Let me just pause for a bit so I can recall what the calculations for it are supposed to be. I mean, it was kind of tricky because it was kind of running it with a cluster size of something, and it wasn't running it with a cluster size of something else, and that shouldn't have been happening. So let me just pause here so I can recall a bit. Oh, now I remember. It was this thread here. I had some issues on setting the cluster sizes on an H100 card, and I couldn't get it to go above 8. And the answer was that I need to set this non-portable cluster size. And that's also the issue with the CuPy. Eventually, I did get it to run with cluster size of 16 on an H100 card, but I had to do it in the native CUDA backend. So that's also most likely the problem here. I think using cluster size at 12 is right, but I also need to figure out how to set the non-portable cluster size. Okay, okay. Let's ask Perplexity whether that got implemented because it wasn't the case a year ago, but maybe things changed by now. Let's see, Perplexity. Is it possible? As of late 2024. Okay, give me a link. Let's do a search for this in the CuPy repo. Settings, we're setting on non-portable cluster sizes. God damn it, it still hasn't been implemented. Yeah, this really is pretty much the reason why I decided to implement a native CUDA backend, so I wouldn't have to deal with this bullshit. Uh, okay, whatever. We okay, now I'm confused. I mean, my plan was to just implement it in implement the kernel. I mean, down the road to implement the couple dictionary kernel in C++ and maybe call it from Python. But if you cannot implement the game in Python, I mean, if you cannot implement the kernels in Python, I mean, in the Python backend, that kind of complicates things. Um, Maybe we could just get rid of CuPy entirely. Let me just pause for a bit. I'm going to the GitHub repos, and in fact, I think they did something to support this feature, support launching of thread block clusters, and this is in the CUDA Python bindings, which CuPy uses. Kernel attribute getter setter. Mm, okay, I think I just leave a message. No, this, okay, let me think a bit. Uh, what exactly do we do here? Like, this should be, I think, a kernel. Okay, you know what? Let's just run this in a debugger. This is like, I think, a kernel, raw kernel, yeah. And here are the options. What exactly am I supposed to be setting here? I mean, I thought that we'd just be working on the game right now, but I'm really getting sidetracked into into CuPy for some reason. I mean, it's not even that important that we figure it out right now. Let's see. Cuda set func attribute launch config. Where do we do Cuda core tests util spy? Okay, can you CuPy as CP run example? Not really. Red Bull cluster. Okay, maybe file changed. With a core experimental device union. So this is grid cluster block stream. Uh, okay, so class launch config. Okay, so where exactly am I setting the grid and the block and the stream? So over here, it's in the kernel. Um, okay, let's see. Where are the blocks and everything else? Transfer block, share memory size, number of registers, function variables. No, wait. This is actually how it works during lunch. And how do I set it explicitly? The core experimental. Okay, let me do a little search in the documentation. Yeah, I think this probably got implemented on the back end, but it probably hasn't been really added to the documentation or the main like CuPy raw kernel. I don't know. Maybe if I look more deeply in here, I'll find kernel options. Kernel. Yeah, who knows? God damn it. No, I mean this is right now. I think this is maybe the only way to launch it. And this max dynamic shared size. No, I mean I think maybe the only choice is to use the Cuda Python library by NVIDIA instead of CuPy directly. Mm. But that means pretty much changing the entire Python backend in order to support this. And I had to get rid of CuPy arrays. I mean, I don't really care that much about that. I've been only using them to really as storage classes to let's get passed into the GPU kernels. Let us assume I had to leave for lunch, and I'm really thinking hard right about now. Like, okay, so it seems I made a serious mistake combining the Python backend with CuPy. So instead of that, I suppose we could kind of change the Python backend so it uses the CUDA Python package instead. CuPy is in fact based on it. Let's see. Prepare the input-output arrays using CuPy, CP random default. Big or large parameters. Oh, I see. I mean, so it has a template. Oh, so it's possible to apply templates to this. Interesting. Launch. The device. I don't know. When I realized that I cannot really launch the kernels from CuPy, right now I'm very seriously leaning towards just dropping Python and doing the host implementation on the of the CuPy algorithm in C++. That could be interesting as well. I'm kind of drawn to it. It's kind of how do I put it? E- Encouraging my adventurous spirit. I mean, I kind of tired of Python. It's kind of if we did it in host C++, what exactly do we lose? I mean, we lose access to the Python libraries, but it's not really like we are even using the Python libraries. So who cares? Um, the main thing that we'll be losing are the Flask servers. I did check out whether C++ has any backend servers, and it does, but they kind of look more complicated to use. compared to the Flask servers. And in C++, the package management is a pain from what I've seen. Just adjusting my camera. I guess it's fine like this. It cannot, when I look at it, it kind of looks at an angle, but I guess it's fine. Let me just turn on the lights to be able to see me better. Okay. I think I'm going to maybe stop here for the day and really think about how I want to do this going forward. Whether I even want to use Python or whether I want to just do it all in C++. Maybe I'll look into this NVIDIA Cuda Python package. We'll see. Excuse me. Let's end the session here, and I'll see you next time. Thanks for coming by. I'm sorry that things didn't go according to plan. I got really sidetracked with these CUDA issues. Even though we shouldn't even be using CUDA for this part of the series. It's very annoying, but I guess that's how things are. See you later.